All right, everybody. I think we're live. This is first time doing this, so we'll see how it goes. This is our live session for AP Physics 2 on electric circuits. So I have a couple questions that I'd like to look at and go over, and we'll jump right in. First question is, it's two circuits that include a resistor and either one or two capacitors. So let's draw that out. See what it looks like. So basically we have a battery. Let's change color, sorry about that. Okay. So we have our battery, and then one resistor and a capacitor, and a second battery, second whole circuit. Also one resistor, but in this circuit we have parallel capacitors. And in the wording of the problem, they tell us batteries are the same. So what does that mean? What can that tell us? What do we know if the batteries are the same? We know that this voltage and this voltage are equal. I could call them V1 and V2, but since they're equal, I'll just use V. All right, so that makes sense. The resistors are equal, so we can put R and R. And they even tell us the capacitors are equal. So this C is equal to C here and the C here. So we know these two capacitors, I should say, will behave differently. The question is, how will they behave? Before I even get into what the question is asking, let's think about what happens. If we first wired this up, okay, so if we had a switch in here or something, let's look at the top one. It's a little bit simpler. What's going to happen? Current will start to flow, right? We'll go through this resistor. When we have current through a resistor, we have a potential difference or a voltage drop. So voltage is going through here. We have a voltage drop. And then the current continues, and it hits this capacitor, right? And as the current flows, basically the capacitor is becoming charged. So that capacitor will charge over time until it's fully charged. They tell us in the problem that this circuit is allowed to come to equilibrium. So slowly this charges up, charges up, charges up, and it charges until capacitor has a plus Q on one side and a negative Q on the other side. Okay, and we know that capacitors will have equal and opposite amounts of charge on each side of the capacitor. Okay, so that's kind of good to know. And if we think about the same situation over here, what's going on? Well, current flows. It begins. At the beginning, we have a voltage drop across the resistor. But over time, both of these capacitors, they'll charge up and current will stop flowing, right? And so we'll have a charge over here and over here. And the question in this problem is saying, well, we want to compare the charge on one of the plates in the first circuit as compared to the charge on one of the plates in one of the capacitors in the second circuit. Okay? And here's the key idea here. Here's the important thing that you need to realize. I think if this was circuits with resistors, you might pretty quickly realize, okay, whatever let's just draw one quick. I'm going to get rid of this resistor for a second, and I'm just going to draw a battery with two resistors in parallel. Okay. So those resistors are in parallel. If I asked you, what is the voltage across this resistor, or what is the voltage across this resistor? Well, you might just be able to see that this side of the battery, our positive side of the battery, is directly connected to one of the resistors. And in fact, that positive side of the battery is also directly connected to the other resistor. And if we do the same thing on the other side, the negative side is directly connected to the opposite side of each of those resistors, right? Directly. There's nothing in between the resistor and the battery. right? Yeah, there's a junction here and there's some wire. Most of these problems we ignore the resistance to the wires. We say they're perfect wires, so we're not losing any voltage there. So if we look, and I'm making up a number, but let's say the battery has a potential difference of 9 volts, then this resistor also has that same difference, right? And this resistor also has that same difference because it's actually connected to the battery directly. Now, slightly different in our case because we have this resistor. And what you know about resistors is that when there's current flowing, they use up some of that voltage. But because they say we wait long enough for this to be in equilibrium, so what does that mean? It means the capacitors have become fully charged. And when that happens, current stops flowing. Okay? There's a gap here. We're not having any electrons jump across this gap. Current can't flow through the capacitors. Okay? It can flow to them and charge them up, and it can create currents in other places, but once they fully charge and they're at a point of equilibrium, current stops. So if current is stopped, then this resistor, in both cases, no longer uses up any of that potential difference. There's no longer a voltage drop, right? We know that there's voltage drop when V equals IR, right? The voltage drop here would be figured out with V equals IR. But if I is 0, then we have no voltage drop. So what does that mean? It's just like what we had here. We say, hey, that side of the battery is basically directly, the same potential is everywhere in this wire. We have the same potential everywhere, all the way up to here. And this wire, all the way up to here. Everywhere in this wire, we have the same potential. And on the other side, even there's nothing flowing, right? But the potential in all of the pink wire is the same. So what can we see here? We can see this capacitor has the same potential difference as this capacitor. And if we go back up to our first circuit, the same is true for that capacitor, right? It's directly connected to the battery. We have no voltage drop across our resistor, and the potential difference everywhere, voltage here, the potential difference across that battery, V, potential difference, sorry, I said battery, across the capacitor, that potential difference is the same potential difference that we have here and the same potential difference that we have here. V is equal in all 3 of these capacitors, and it's equal to whatever the battery is. And since the batteries have the same V, all V's, all potential differences, once we've reached equilibrium, are all equal to each other. And now we can answer this question. If we want to know how much charge is on this plate as compared to this plate, which one is holding more charge? Well, we know that for capacitors, C equals Q over V, right? And that's straight off of our reference table. And we just said this. V in both circuits is the same. They told us in the problem it was given that C is the same. So C in both circuits is the same. Okay, well if we rearrange these, the Q is always going to be C times V. And if C is the same and V is the same, Q is the same in both cases. So this positive Q equals this positive Q, which equal this positive Q. Okay. Now, there's a question here that wasn't asked, and we could talk about it more. We'll probably hold off right now, but maybe you could think about this and see if you can answer it. How much total charge is being held here? Or another way of thinking about this, what is the equivalent capacitance for these parallel capacitors? Okay? There's a way to figure it out. There's a formula you can use, and hopefully you can answer that. So give that a shot. But for this question, when they're asking how do these charges relate, charge on this plate versus charge on this plate, those charges are equal. All right, great. Seems like we're off to a pretty good start. Let's see what else we have. I have another problem I'd like to look at. So this problem, let me pull it up. Okay, we're going to have another circuit we're going to draw here. All right, so we have an EMF, they label it E for us, with a resistor 1, resistor 2, resistor 3. Then they throw in an ammeter. Let's erase this. There's a switch here. Okay. So let's leave the switch open for a second. So there's an ammeter. And here's a capacitor out here. Okay. And they tell us some information here. Let's read what they tell us. A battery of EMF E, or epsilon, is connected to 3 resistors, a switch, and a capacitor, as shown in our diagram. The resistance of resistor 1 is greater than that of resistor 2, which is greater than that of resistor 3. So let's write these. I didn't put my numbers in here. 1, 2, 3, and this is the biggest, so I should say R1 is greater than R2, which is greater than R3. Okay? Maybe it'll be important. They're giving it to us, so let's make sure we understand it. After the switch is closed and the current has reached a steady state, that's that point of equilibrium that we talked about before, right? Which means if this capacitor is charging, now it's become fully charged. Okay? There's no... yeah, that's it. It's fully charged. It has as much charge as it's going to have on it. Okay, so it's at a steady state. Doesn't mean that, as in our other case, steady state meant that current stopped. This doesn't have to mean current stops. It just means that things aren't changing, right? So capacitors are fully charged if they're going to be charged. Okay. Sometimes, in our previous problem, steady state meant current stopped, right? In this problem, you'll see in a moment, current is not going to stop. So let's look. So we've reached a steady state. And then they tell us an ideal ammeter is connected between points X and Y as shown. Okay, so we see that ammeter. We've already drawn it. The circuit is again allowed to reach a steady state. So, things are happening. I drew it out here with an open switch. That's not exactly what happens. This is going to get a little confusing. No ammeter. Switch is open. Close the switch. We'll charge up our capacitor. Now we reach a steady state. Once we're at a steady state, then we put in an ammeter. Okay? All right. The circuit is again allowed to reach a steady state. So things are going to change. Maybe this capacitor charges up more. Maybe things discharge. We'll see in a moment. We reach another steady state. And then we asked, which of the following correctly indicates the reading on the ammeter and explains why it's that reading? Okay. So what is this ammeter going to read? When we look at this, we can think about things like junction rules, right? So don't forget about, our basic circuit information. We can, if we had a way of figuring out a total resistance or something, we could maybe do an Ohm's law and figure out, okay, there's some current, I, I'll call it I over here. This is our total current from our battery, right? Now, when that current gets here, the only thing that can happen, this current can split into 2 pieces. And these 2 smaller parts have to add up to this. This is what we call the junction rule. The current into a junction has to be the same as the current going out of the junction. So these two have to add up to that one. Okay? And then we have this one reaching another junction. And that can split again. So the downward through 3 could be plus this across the switch, which is now closed. Those two currents have to add up to this one. Okay, we have another junction, and the current could split here, and these two currents have to add up to this one. All right, so far so good. We know the junction rule. Now, there's a key piece of information here that we have to think about. And it may not be 100% obvious to you right away, but if you know anything about how we wire circuits and put ammeters and voltmeters into circuits, this should look a little funny to you, right? It wasn't here before, and then we just added it in. Okay, let's go to an old-fashioned, very simple battery resistor circuit. In this circuit, if we wanted to add a voltmeter, we want to read across the resistor, we would have to attach to find the difference of this point above and this point below, right? That's why voltage is called potential difference. We're comparing 2 points in our circuit, and we run that through our voltmeter, right? What would happen in this case if we, let me slide this up a little, if we didn't have a voltmeter, we just used a piece of wire? Kind of backing around the answer, the information that we need to know here by talking about voltmeters. Hopefully you can think of it before I say it. What if we just connected, instead of a voltmeter, a piece of wire that jumps over this resistor? What if that resistor was a light bulb, right? What would happen? Without the wire, light is shining. If you add the wire here, you have what is known as a short circuit. Your current's going to go and take the path of least resistance. It's going to bypass your resistor. Because in our circuits that we draw, our wires have, they're perfect conductors. There's no resistance at all, so this current is very happy to just flow around this resistor, which is hard to get through, right? Well, that's not what happens here. As a matter of fact, if this voltmeter is what we call an ideal voltmeter, then this light bulb, if it was a light bulb instead of a resistor, wouldn't even dim. None of the current, we're getting into ideal situations, but I mean, technically to have a reading, we have to have some current. So, but when we call this an ideal voltmeter, we're basically saying the resistance here, it's approximately infinite resistance. Infinite ohms of resistance. Why? Because we only take a teeny tiny bit of current to take our measurement, and it barely affects anything else going on in our circuit, right? That's what we want voltmeters to do. We want them to not affect what we're trying to measure. Now let's think about that with an ammeter. If we were trying to measure, let's draw it again. Maybe I'll do it on this side. So these are voltmeters. Let's do an ammeter. Same simple circuit, battery resistor, and we want to know the current through this resistor. Well, first, if you tried to wire your ammeter, and maybe I'll just draw it over here, same setup. I do an ammeter across just like I did my voltmeter. What did we just say about the junction rule? Is it possible for it to measure the current through here? Current is charges that are passing by every second, right? Coulombs per second. Could we count those coulombs per second? Well, some of the current would be going here, and then we have a fork, a junction. Some current would go through the ammeter. Some current would go down through the resistor. We want to know what this is, and we don't want to steal any of it through the ammeter. Now you might think, well, maybe could we just say it's just like a voltmeter? It has infinite resistance, so nothing goes through it, and it doesn't work like that. Unfortunately, this will not give us any kind of reading. We need to do an ammeter, the charges need to be passing through the ammeter. Think of it like cars going down your street. Well, the charges that are passing through the ammeter are the ones that are being counted, right? And we need to count those coulombs per second. So this doesn't work. What we end up having to do is we have to disconnect part of our circuit and then reconnect it, rewire it with our ammeter being part of our circuit, right? So now we can see the current going through our resistor is also going through our ammeter, okay? And what do we know about figuring out current and resistance and voltages and voltage drops and all of those things, right? We don't want to affect this circuit. We don't want to change anything about it. But if you put something in series, isn't it going to use up some of that potential, right? Some of that voltage, isn't it some of it going to be used to get through the ammeter? And in fact, it does a tiny, tiny bit, but we want to minimize how much voltage gets used by the ammeter. So how can we minimize how much voltage is used by that? Well, if we want the current to go through there, right? But we want V to be as small as possible, but the current is going to be whatever it is in the circuit, right? We want to measure whatever it is. If it's big or small, we want to know what this is. That's what our ammeter is doing. But we don't want to have a big voltage drop. That means our resistance has to be really small. And what I was trying to kind of point to before is that ammeters, they have approximately no resistance. R is approximately 0 ohms. Now, coming back to this circuit, what happens if there's no resistance in part of our circuit? Well, current's just going to flow through that and bypass everything else. So, let's trace the path of our current in this circuit. Current flows from the battery, flows through here, and now it's in this part of the wire. If it was pushed hard enough, it could get through a resistor or get through this resistor, but guess what? It has a path where it doesn't have to be pushed at all, right? Our ammeter has no resistance whatsoever. This ammeter is creating a short circuit. So whatever current is going through, we'll call this I1, the current through resistor 1, is the same current that we will measure on our ammeter. We're going to measure whatever that current is. No more current will be flowing through resistor 1. No more current will be flowing through resistor 2 or resistor 3. And as a matter of fact, if this was all charged up, now this isn't part of the question, maybe you can think about it. Remember what we said at the beginning. This was first wired this way. The switch was closed. In that case, the capacitor got charged up. It got charged so that, just like in our last problem, one side of our capacitor is directly wired. Oh no, it's not. It's a little more challenging than that. We could do some calculations. I'm going to leave it to you. But you'll get a potential difference across your capacitor. So it does get some charge. It's not going to be exactly this because we can have current flowing even when current stops flowing through here when it's fully charged. Right? When it's fully charged, this fully charges, current stops flowing in here, and it's acting like it's not even there anymore. But it's still fully charged. Yeah, it's a complicated problem. But then when we add our ammeter, think about all of the charges built up here, Q, positive Q, and our negative Q, whatever they are. Now they are directly wired to each other. Is our capacitor going to continue to hold a charge? I'm going to put that out there and leave it there, and maybe you can think about the answer to that. And I think those are two great problems to give you a little bit of better understanding of electric circuits in AP Physics 2 and how capacitors can be a little bit better understood. Hope that helped. Let me know what you think. All right, take care.